You are using the computer audio. Start video. I think I need to turn that up a little bit. Yeah, maybe like that. That's pretty good. Not too bad. Not too bad. I wonder if I have any students. Let's see. Nope, no students. We're 10 minutes early. So I could write on here what we're going to do today. Yeah, that's an idea. What are we going to do today? Well, we're going to study deformation, chapter 4. Deformation from stress and from temperature. Yeah, that's what we're going to do. So the topic is deformation. And you can get that, it can happen from stress or from temperature. Yeah, well, we'll do both. Okay, well, that's the topic. Now, what about homework? Now, there's a homework. Homework number 13. Is due Friday. It's problem 4.3, and I need a diagram. It's due Friday. And then homework number 14. Homework number 14 is it's due Sunday. Yeah. So you got a little something to do to send me. Okay. Well, let's see if there's anybody on here now, if I've gained any students. Uh-oh, I bumped this thing. So I need to adjust it, I guess. That's pretty good. Let's see here. Nope, we don't have anybody. It's just me talking to myself right now. Hopefully they didn't forget there's a class here. Of course, we're 6 or 7 minutes early. All right. If you'd show up early, you could ask me some questions and get, hey, we've got a student. Ashley hasn't let me down. Ashley's shown up. Good going, Ashley. It's just you and me, Ashley. Nobody else yet. Did you have any questions or comments, Ashley?
No, not at the moment.
That's fine. That's just fine. I don't know what kind of day it is. I'm going to look out the window and see if it's going to be a beautiful day. Oh man, the sun's out. It's a beautiful day out there. Beautiful days. Sunshine. Not raining right now. It's a beautiful day. And we're in chapter 4. And that's all about deformation. Let me get my my book here and see what they said chapter 4 is all about. Well, the title is axial loads. They're talking about members that are long and slender and under tension or compression. Pretty much what the topic is. Axial loaded members. Okay. Let me see if anybody else has showed up yet. No, it's just me and Ashley. Ashley, what's your major?
Mechanical engineering.
Oh, that is wonderful. That is just wonderful. You'll get a good job. It'd be nice to have a good job.
Yeah.
They exist. They're out there. Okay, well, let's see. I know what I'm going to talk about. We're going to talk about deformation in this chapter. What else? Well, there's two kinds. There's deformation caused by tension and compression, and deformation caused by temperature going up or down. What else is in this chapter? Let me look and see. That's pretty much it. Sounds pretty easy. Yeah, and the next chapter we'll study next week is on torsion, where you're twisting things, but we're not twisting anything yet. Now, what have we been studying? Let's see. Well, we've been studying the properties like the modulus of elasticity, for instance, the modulus of rigidity, the modulus of resilience, the modulus of toughness. We've been studying those. But now we're going to study deformation. Oh gosh, class starts in 1 minute. Oh, we've got Nicholas. Nicholas is with us. Yay. Oh, look here. We got a good crowd. Alex and Ben and Mohammed. Alex, Ashley, Nicholas. We got a good class already. Good going. How about you guys? You have 1 minute before class starts. Did you have any questions? Any questions? From anybody? Trying to get my whiteboard back up here, but I can't seem to do it. There, wait a minute. There we go. There's my whiteboard. How do I get rid of? Yeah, that looks pretty good. Okay, here's your last chance. The time is running out. Oh no, time is up. It's time to start. Well, I listed your homework here. This is due Friday. This is due Sunday. I even have the page numbers there someplace. Let's see if I can write those down for you. This one's on page 135. And this one is on page 159. But it isn't due till Sunday. So that's in your Blackboard there. You can look it up. You don't need me to write that. I just thought I'd tell you for sure that you have homework. I was looking for your next exam, but it's ways off. I wrote it down. I think it's the 13th of October. Does that sound right? Exam. No, it's the 15th of October. Yeah, a long ways off. Your exam is the 15th of October. But you know what? October is Thursday. This is Tuesday. That's right, isn't it? I don't know. Let me get my calendar here. Yeah, here's my calendar. And yeah, October is Thursday. So it's not that far off. The exam is the 15th of October. It's chapters 3, 4, and 5. We're in chapter 4 today, and we better get going on it, hadn't we? Because we got to study 3, 4, and 5 before that exam. Okay, anybody want to say anything? Otherwise, we'll just launch into the exciting world of deformation. Okay, well, I'm going to erase all this. You don't need this. It's all in your Blackboard syllabus or schedule there. Now, the symbol for deformation is this Greek letter delta. We've seen it before. It's a little Greek letter, kind of looks like that. The capital Greek letter delta, you know, looks like that. But see, that's the capital letter. And we're looking at the little letter here. and you've seen the equation for it. It goes like this. Strain is equal to the deformation over the length. So the deformation is just equal to the strain times the length. Now we have a lovely equation with strain in it that goes like this. Stress is equal to your modulus of elasticity times strain. That equation has a name, by the way. Let's see if anybody ever listens to me. I'm going to go to my friend. Shane. Shane, unmute and say hi. Unmute and say hi, Shane.
Hi.
Yeah. Hey, Shane, do you remember the name of this important equation? Maybe the most important equation in the course. What's the name of it?
That was a Hooke's Law.
I'm sorry, I didn't quite hear you.
Hooke's Law.
Yeah, it's Hooke's Law. Good going, Shane. See, you guys do listen to me after all. I wonder if they can read that. Pretty bad writing, but yeah, there you go. There's Hooke's Law. Well, see, using that, you could write this as sigma over E times L. Can you get to here with me? See that little epsilon is equal to sigma over the modulus of elasticity. Yeah, you can get there, right? You're doing okay. Okay, great. And then you guys all know that stress is equal to normal force over area. So see, you could write this as normal force over area. Can you get to here? Can you substitute in for that little sigma there and get your NL over AE? Now in some books, they use P for normal force. This book uses N for normal force, but in some books, this is the way I learned it. Deformation is PL over AE. I really like that better because what would you rather do? Practice your piano lessons or your violin lessons or whatever you're supposed to be practicing, or go outside and PLAE? What would you rather do? Well, some of us would rather go outside and PLAE. And that's easy for me to remember. But this book uses NL over AE for deformation. But it helps to have something to jog your memory there. So now we have the lovely equation for deformation, only it's often written like this. Now, am I making that up or is that in your book? Let me snoop around here in your book and see if I can. Yeah, there it is. This is in your book. It's on page 126. Now it turns out that the normal force might possibly be a function of its position along this member that we're talking about, these axially loaded members. And the area might be a function of where it's located on the member. And even the modulus of elasticity could vary. Let me see if I can show you an example. Well, they have some in the book. Yeah, let's find you one here in the book here. Look at problem F41. Yeah, here we go. Yeah, that'd be okay. We're going to look at problem F41. And they have this, what they call an axial loaded member. It's an axial loaded member. And I like to put my forces in red. This happens to be on page 134. And I'm going to put my forces in red. They said there was a 40 kilonewtons force there. And let me make that a little smaller, maybe, because they have a 50 and a 50 kilonewton for two of them there. But see, that makes 100 going to the left and 40 going to the right. Guys, we can't have that. Our forces have to add up to 0. So you'll have to have a 60 kilonewtons acting on the left-hand side of your member there. I hope that makes sense to everybody. I mean, they have to add up to 0. Look, 60 and 40 add up to 100, and 50 and 50 add up to 100, so the forces add up to 0. That's good. They have to. But what is the deformation? Now, they label this A, B, and C. And they want to know the displacement of C with respect to A. See, they want to know the deformation going from A to C. Well, the way you have to do this is you have to make a diagram. You have to make a normal force loading diagram. Now, we've done these before. And the secret to making a normal force loading diagram is you have to take a section. See, if you section this through in here someplace, you're going to have a 60 kilonewton internal force. See, these are external. That 60 is external. Those 50 kilonewton forces are external forces. That 40 is an external force, but you have internal forces. Inside here, you'll have a 60 kilonewtons, but it's got to go to the left, which means you've got compression. So here we go. We're going to draw our normal force loading diagram. This is called a normal force loading diagram. That's the name of it. And these are important. There's actually 4 different kinds of loading diagrams. There's the normal force loading diagram, the shear force loading diagram, the bending moment loading diagram, and the torque loading diagram. They are terribly important because they give you the internal forces. Well, can you see that you'd in here, if you sectioned it in here, here I'll draw it for you. If you sectioned it in there like I just did, there's A, and we know there's a 60 kilonewtons, and you always make a left-hand section. Can you see that you'll have to have a 60 kilonewton internal normal force? And can you see that it's pushing? It's not pulling, it's pushing. Pushing is compression. Compression is negative. This is your normal force versus your X. So you got a negative 60 down here someplace, negative 60. And that's true all the way to here. Negative 60 kilonewtons. Does that show up? Yeah, that does. And then what happens is it jumps up 100. See that 50 and 50 add up to 100. And what you have here is for the rest of the way, you have 40 kilonewtons of tension. It's positive. See, it's positive here, negative here. That's a plus 40. Now, if you want to color this in and make it pretty, that's fine with me. Here, let me color in this diagram. There you go. We colored it in and tried to make it pretty. Yeah, get your crayons or whatever. But now they want us to use this equation. This equation here. I haven't really talked about this much yet, but let me just mention now. See, the area hasn't changed on this piece, on this member, and the modulus of elasticity hasn't changed. But the normal force has, because here it's compressive 60, and here it's tension 40. So you would not be able to pull that normal force out, but you could pull out the area and the modulus of elasticity. You could pull them out because they're constant. We'll show you some other examples. Let me erase that. I'll come back to that. And we're going to find the deformation. But since the internal force changed, you're going to have to go minus 60 times, in this problem on page 134, that's where we are. This is 0.6 meters, PL over AE, and the area is pi over 4, 0.020 squared times E. Well, you have to look up E. It's 836. We're dealing with the metric system. So you look in the back of your book and it says 200 gigapascals. It's 200 gigapascals. But see, it's negative because it's compression. But then you have a positive tension of 40 times 0.4. Getting a little bit lazy with my units, but I've put them here, so it's okay. Well, I left out those units there. Shame on me. Let me put those in. Pi over 4, 0.02 meters squared times E. There you go. Now that's plus and that's minus. And now we have to put all of this in our calculator to get our deformation. Okay, I want everybody to do that. I'm going to do it. We have an equation here. See it? It's a deformation equation. And we don't know the answer yet. We'll put a little question mark right there. I'm going to do it. I want you to do it. And we'll see what the deformation is. Go for it. Don't forget, kilo means e to the 3. Well, I got an answer. I'm hoping you got the same answer. By the way, if you just tuned in and wondered what we're doing problem F 4-1 is what we're, yeah, here it is. It's problem F 4-1. It's on page 134. And I plugged in all this stuff and I got my deformation. And what I got is minus 5.7 rounded off 10 to the minus 4 meters. Now you could write that as negative 0.573 millimeters if you wanted to. Let's look and see how we did on that. See what the answer book says. They do these fundamental problems in the back. And they said F4-1. Uh-oh, I'm not getting that answer. F4-1. Uh-oh, something bad happened, guys. They're usually right, too. The answer in the back, I must have done something wrong. The answer in the book says, it does say minus, that's good. And they said 0.318 millimeters. Now, I didn't get 0.318. Maybe I need to do mine again. Anybody get their answer or my answer?
I got 0.318.
Bless you. I'm going to try mine again. I must have pushed the wrong button. Okay, here we go. I'm trying it again. No, I get the same answer again. I wonder what I'm doing wrong here. Did they say this is the diameter, the 0.02? Yeah, I got that right. And it is 200 gigapascals, isn't it? A36, go to the back, it's 200, yeah. 200 gigapascals, that's right.
Professor,
Yeah.
I don't think you're adding the second part of it, the 40 part of it, because I got the 5.73 for the first part, but then you add,
Oh,
I
I'm only
don't know.
doing that.
Correct.
Hey, you could get a thank you point for this. Let me try this one more time here. I'm not quite ready to give up. 60 e to the third is something, and then you put a minus sign on it, times 0.6 divided by pi times 4, 0.02 squared. Now wait a minute. I'm going to go ahead, I'm going to add these two, and then I'm going to divide. They both divide by the same doggone thing, so let me start over. 60 e to the third times 0.6, and that's negative, plus 40 e to the third. You know what? I bet that's what I did. I bet I didn't put the kilonewtons on this. I don't know. Let me try that. Plus 40 e to the third times 0.4. And then I'm going to divide by pi times 4. Divide by 0.02 squared. Divide by 200 e to the ninth. And boy, Jove, you get 0.3183 millimeters. And the book was right, and they usually are. This is your deformation. In other words, it got shorter. See that 60 kilonewtons of compression was the boss term. And thank you so much for speaking up. I'm going to put a thank you point right in that corner there. It's nice when the students are more intelligent than the professor. You know that? Makes it nice. Okay, well, we got that under our belts.
Mr. Griffin,
Yes, go ahead.
can you explain the diagram one more time, please?
Oh, yeah, let me do that. This is called a normal force loading diagram. And what it depicts, Mohammed, is the internal forces. See, that 60 is external. That 50, those are external. That 40 is external. But we want to know what the internal. You understand what internal, external is, right, Mohammed?
Yes,
Yeah,
yes.
Okay. Well, see, right here, we're trying to find what's going on right there. Now, look at this diagram. This is what they call a left-hand section. You have the 60 kilonewtons external, but right in here, you have to have a 60 kilonewtons going to the left for equilibrium.
Yeah.
Going to the left is negative. Do you see why it's negative?
Yes.
Now, I didn't do the section in here, but let's do it. Let's section this in here. Let me just make a little room here someplace. And we'll do that section. Now, you're supposed to do a left-hand section. So I'm going to do it the way you're supposed to do it. Now I'm going to draw all the external forces on this. We have 60 going to the right. We have 50 going to the left here, 50 going to the left here. Now, what do you have here? Can you see that you need an internal force of 40 kilonewtons internal? It's in here. You have to have that internal 40 kilonewtons for this section, this left-hand section, to be in equilibrium. Now that's going to the right. Going to the right is positive. See, this is positive. See, what you have here is tension. Up above the axis, you have tension. That is pulling. See, tension pulls. Tension pulls. Compression pushes. Tension pulls, compression pushes, and you have 40 positive. So this thing jumps up. Now notice it jumps up 100 from minus 60 to plus 40. That's a jump of 100. You know why it has 100 jump? Well, because you have 50 and 50 external forces, and that makes a jump of 100. And there's your normal force loading diagram. Mohammed, do you understand the normal force loading diagram now?
Yes, sir, I got it. Thank you.
Earth calling Mohammed.
Yes, I got it. Thank you.
Yay, you are so very welcome. Okay, well, good. We did that one. Now back to this other equation here. Let me make a little room. Anybody else have a comment or question? And thanks to our excellent students, we got the right answer. That's always nice. And I was just doing a algebraic or a calculator mistake and getting the wrong answer. Now back to our equation. In general, now this is the general equation. It goes like this. Now here's the thing, if the normal force is constant, you can bring it out. And you can write this, you can write it like this. See, if something's constant, you guys all took calculus, you know you can bring it out. Now, if the area is constant, you can bring it out. You can do this if n is constant. If the area is constant, then you can bring it out. And you have this equation here. See, I took the A and I just pulled it out. Here I took the N and I pulled it out. Now, if the modulus of elasticity is constant, it's not always constant, guys. But if it's constant, then you can pull it out. And you have this equation here. Of course, you know what that is. When you solve that, you'll just get NL over AE. And that's the equation that we're studying right now. Deformation is equal to NL over AE. Unless you're in one of my other books that I studied it with many years ago. And then it's PL over AE. If you use a different symbol, but we don't care. We're fine with that symbol. But you need to be warned that if any of these things vary, if the normal force varies, if the area varies, like, let me give you an example. The Washington Monument is, there you go. I drew you a picture of the Washington Monument. There it is. Actually, it's more like it's obviously wider at the bottom than at the top. Not a very good picture, but maybe you get the idea. See, it's wider down here. The area, actually the cross-sectional area is, it's like that. But up here, the cross-sectional area is smaller. And it gets smaller as you get to the top. Just out of curiosity. We got a lot of students. Have any of you guys ever gone up to the top? Who's gone up to the top of the Washington Monument? Speak up. Anybody? We got all these students. Surely somebody's been there. Jackson, have you been to the top?
No, I haven't even been there.
Would you like to?
I haven't asked yet.
It'd be kind of fun, wouldn't it?
Walked around the bottom of it.
I think they have an elevator that goes up to the top now. Now, when I went up to the top, there's a little window up there, and you could throw pennies out. but they don't let you do that anymore. I mean, think of what would happen if one of those pennies hit somebody in the head. That could be fatal, you know it? No, you can't throw pennies out the window anymore. It's really high. From up there in the top, you can see the roof of the White House. You're looking down on the roof of the White House. But now the reason why I'm mentioning all this is the area varies. See, the area up here is smaller, and the area down here at the bottom is bigger. And so you can't pull that area out like we did. It has to stay inside the integral. You understand that? Well, we could talk about that more, but you got the idea. This is the general equation here, and this is the simple equation. It's pretty simple. That's when none of these things vary through your piece. Okay, well, do you have any questions on that? Yeah, I don't guess there's any questions. Probably ought to do another problem though. Make sure we feel secure about this. Do we have lots of time? Yeah, we're doing great. We got lots of time. Let's do another problem here. Now, I don't want to do your homework though. I don't think this is your homework. We'll do this one. This looks pretty good. Now this is F. Do I want to do that one? Just a minute. Let me find the one I really want to do. Maybe we could do, yeah, let's do this one. Yeah, this would be a good one. And now this one's 4-3. No, that's on your homework. I don't want to do that one. No. I don't want to do that one. That's on your homework. How about this one? This looks pretty good. These are all good. It's so hard. It's so hard to decide. Well, we'll do this one. This is F42. Fundamental problem 4-2. Now you know the drill. You draw the free body diagram. And then you put all the forces on there. Now we got to make sure these all add up. They have to add up to 0 or we're in the wrong class. Now let's make sure these add up to 0. What we're doing problem 4, fundamental problem 4-2 right now. It's on page 134. Now if you have 10 going to the right and 15 going to the right and 15 going to the right, that makes 40 going to the right. You got 20 going to the left and 10 going to the left and 10 going to the left. That makes 40 kilonewtons going to the, yeah, they add up to 0. So we're okay. Yeah. All right. Now we're going to draw the normal force loading diagram. And the way you draw a normal force loading diagram is you take left-hand sections. Let me write that for you. You take left-hand sections. If you want to draw a normal force versus your x coordinate loading diagram, the way you do it is you take a left-hand section. Okay, well, if you sectioned it in here, can you see that the internal normal force is 10 to the left? So that's minus 10. Here we go, minus 10. Anywhere in there. I don't care where you section it, it's minus 10. Then it takes a 20 kilonewton jump up. So it goes up to a plus 10. See, if you section it in here, you'll have to have a 10 kilonewton going to the right internal normal force. Those are supposed to be equal. Need to make that a little smaller, I guess. There we go. We're doing great. We're making our normal force loading diagram. See, that's minus 10. This is plus 10. We're doing these in kilonewtons. Then if you sectioned it in here, you know what? You got a jump of 30, but you're going down. So it goes down here to minus 20 and over to here like that. This is minus 20. Okay, and then you can color it pretty if you want. I think I'll color mine blue. Okay, we got a nice blue color here. And the blue color here. And the blue color here. There you go. Do not come back up here to 0. It doesn't go back up to 0. It's still got 20 kilonewtons of compression everywhere in here. It doesn't go to 0. So do not take this and come back up here to 0. It doesn't go to 0. Neither does this. This doesn't go up to 0 either. It starts right there. It has 10 kilonewtons of compression even at the very left-hand side of that. Okay, great. Well, we did that. That's how you that's how you draw normal force loading diagrams. So what? Well, they wanted us to find the displacement of D with respect to A. Well, D is over here and A is over here. So here goes. We're going to write it now. So we're going to go minus 10 times 0.4 divided by the area. Pi over 4, 0.02 meters squared. It's aluminum. We got to go to the back and look up aluminum, alloy of aluminum, and it says 0.02 68.9 gigapascals. 68.9 gigapascals. Okay, well, now we're going to do this one in here. Well, see, that's going to be a plus 10 times, now wait a minute, it's 0.4. This distance is 0.4 meters. They're all 0.4 meters. And then that's a plus because it's under tension. See, that's tension. Plus is tension. But wait a minute, the area changed on us. It's in here, we're looking at a section of pipe. And the area of that section of pipe is pi over 4, 0.04 squared minus 0.03 squared. If you don't understand that, I'll be glad to go through it. You have to subtract this area inside because it's not there. We're just dealing with the outside, the pipe there. And so that goes here, pi over 4, 0.04 squared minus 0.03 squared. And don't forget the modulus of elasticity, but it's the same. It's the 68, oh gee, I'm running out of room here. 68.9 gigapascals. And I haven't even gotten to this part here yet. We'll stick it up here. Now wait a minute though, it's going to be minus 20 kilonewtons times 0.4 divided by what? Divided by, well, it's the same diameter, pi over 4, 0.02 squared, 68.9 gigapascals. So what we got to do is we've got to add up all of this stuff here, and we should have the deformation. Okay, let's see if I can do this right. Remember, I goofed up last time. Can you read all that stuff? Probably. It's a little messy, sorry. Add that, there's two negatives and there's a positive. Add all that up and we should get the answer. I'm going to do it. I want you to do it. And we'll see how we come out. Here goes. I probably should put kilonewtons right there, or else I'll forget to multiply. Well, I don't know, guys. I did all that. I'd have to do it several times to feel confident about it. But I'm getting a negative. In other words, the whole thing's gonna shrink. The whole thing's gonna shrink. I'm getting a negative 0.4488 millimeters. I'm gonna see what the answer book says. Maybe I got lucky. This is problem F42. We're doing problem F42. And the answer book says negative 0.449. Hey, even a blind squirrel finds a nut now and then. Believe it or not, I did that one right. And the book says negative 0.449 millimeters. Do you have any question about that one? Okay, well, let's go on, I guess. If you're happy, are you sure you're happy? Let me put it this way, did anybody get that? If so, say, uh-huh.
I got it.
There's two of us.
That's what I got.
Yeah, good going, guys. Well, that's how you do it. Okay, well, let me show you something else here in this chapter. And this is called statically indeterminate problem. I'm trying to find where it talks about that. Statically indeterminate problems. Yeah, there it is. You know how we go over to OSU and have meetings and talk with the professors over there that teach the same classes. Well, they teach this same topic called statically indeterminate problems. It's on page, in your book, it's on page 140. And the topic is statically indeterminate Is it A? Yeah, indeterminate. I'll just say problems. Statically indeterminate problems. And over there at OSU, or you could go anywhere, you could go to Harvard or MIT, and they would study statically indeterminate problems. And what they are is problems that cannot be solved with statics alone. And I'm going to show you an example here. This is problem 438. And they've got a cord here, or piece of steel maybe. Yeah, it's steel. It's steel wire. And wire AB is 60 inches long. Now this is wire AB. It's 60 inches long. Okay, and oh, wait a minute, they have a 2,000 pound weight sitting here. 2,000, that's a ton, 2,000 pounds. on this 60-inch wire. Now they have another wire. This is sort of a backup wire, kind of a safety type deal. Now this wire here is a little bit longer, and it's connected at C up here. It's got some slack in it, and the reason why is that wire is 60.04 inches long. Now I've exaggerated the slack in it so that you can tell. See, it's if you were holding this 2,000 pounds, well, I wouldn't be holding it. That's a ton. I can't pick up a ton. But see, it's longer. And as you put this load on here and increase it up to 2,000 pounds, both wires are going to stretch. But here's the statics equation. You know how it works. The sum of the forces equals 0 in statics. And so the force of AB plus the force of AC will equal 2,000 pounds. This is your statics equation. But see, you can't solve it because even though we know when you put that load on there, they're both going to stretch. They're both going to stretch. But we don't know how much. And we don't know how much each one is going to hold. But they have to add up to 2,000. They'll add up to 2,000. You need another equation. Now, the other equation is called the compatibility equation. It's got a fancy name. I think that's how you spell compatibility. Maybe we should look that up. Yeah, that's right. I spelled that right. Compatibility, yeah. This is called the compatibility equation. And I find these are kind of tricky. But I'm thinking that this AB is going to stretch more than the AC. I think the deformation of AB is going to be the deformation of AC plus 0.04 inches. I think it's going to have to stretch more. Think about it. See, as you say, you start putting this load on a little bit at a time. Put on 100 pounds, 200 pounds, 300 pounds. This AB is going to start to stretch. AC isn't going to stretch yet, not until you've stretched 0.04 inches. Then AC will start to stretch. So does that make sense that the deformation of wire AB, it's going to be bigger. It's going to stretch more than AC because AC is limp to start with. It hasn't stretched a bit till you get to 0.04 inches of stretch, and then it'll start to stretch. This is called the compatibility equation. And so what we have is a statically indeterminate problem. Now, more complicated ones, here, let me write this for you. You have one, on this problem here, you have one, no, just a minute now. You have, yeah, see this equation here? You have one equation and you have two unknowns. Well, you can't solve one equation with two unknowns. It's statically indeterminate is their fancy word. Now, a more complicated problem we could run into is where you have two equations and three unknowns. you can't solve it either. See, if you have 3 unknowns, you need 3 equations, and so forth. If you had 3 equations and 4 unknowns, you can't solve that. You need another equation. See, if you had 4 unknowns and 3 equations, you can't do it. But if you had another equation, if you had 4 equations and 4 unknowns, you could do it. The other equation that we need to solve these statically indeterminate problems are called the compatibility equations. And they involve the deformation delta. Well, there it is. We're going to write it out and we're going to solve this. Now, here's my thinking on this. AB is going to be f of AB times its length divided by the area. What's the area? Let me look and see here. It says here, it says here, the area is 0.02 inches squared. They gave it to us. Wasn't that nice? It's 0.02 square inches. Now we need the modulus of elasticity. Well, it's steel. It's 29 MSI. Now they write it as 29 times 10 to the third KSI, but that's the same thing. Do I need to explain 29 MSI to anybody? Well, I think we're done with that wire AB, but see, we've got an equation here. Now we've got to write this deformation of AC. Well, that's going to be the force of AC times its length, 6004, divided by the cross-sectional area they gave us. Wasn't that nice of them? And that has the same modulus of elasticity. Okay, now if you can read all that, guys, we have 2 equations and 2 unknowns. Now let me circle these. This is the statics equation. This one here has got a fancy name. It's a strength of materials. It's this class here. It's a strength of materials equation, but they gave it a fancy name. They call it the compatibility equation. This is it. You're looking at the compatibility equation. Now we're going to solve these 2, and we're going to find what these forces are and how much the thing actually stretches. But we need some room to do it in. Let me make some room here. But now you've heard about statically indeterminate problems. I asked the fellows over there at OSU, and they feel that this is important. And a lot of you are going to OSU, and so that makes it important, doesn't it? Okay, well, we're going to do some algebra now. Here's my plan. Can you see if you can get to here with me? F of AB is equal to 2000 minus F of AC. Okay, can you make it from here to here? Can you make it? I know you can. I know you can make it to there. Okay, so what we're going to do is we're going to substitute that in. All right, we can do that. All right, substitute that in. See that F of AB? Put it right here. So what you've got is 2,000 minus f of AC times 60 divided by blah, blah, blah. Equals this stuff here. FAC times 6004 0.02 29 MSI plus 0.04. All I've done is rewritten this equation and substituted in for FAB. FAB is 2,000 minus FAC. 2,000 minus FAC. There you go. Now all we got to do is solve that. And I need this room, so let me make some room. Here we go. We can do this. I think what I'll do is I'll take the 2,000 times 60 divided by 0.02 inches squared, 29 MSI, minus 60 FAC. You know what, all of that's all over the same denominator, isn't it? Equals FAC times 6004, same denominator, plus 0.04. I'm just doing some algebra here. Now I think what I'm going to do is I think I'm going to take this but I'm doing algebra now. I got that, and I think what I'm going to do is I'm going to subtract 0.04 from it. That's legal, but it's just algebra. And then I'm going to add this, I'm going to put it over on this side. And so over on this side, what you'll have is 60 FAC over that plus FAC times 60.04 divided by 0.02 29 MSI. All right. Now, one more step and then I'll shut up and let you guys solve this. I'm going to go ahead and get that number in my calculator. 2,000 times 60 divided by 0.02 divided by 29 e to the 6 equals 0.206 something. And when you subtract the 0.04, what you'll get is 0.16689, maybe round it off to 7. I just put all that in my calculator. And that's equal to the 60 plus the 6004 FAC divided by 0.0229 MSI. All right, get your calculators out. I know you can do this. We have an equation with only one unknown now. And we're going to solve for FAC. Here we go. We're going to find FAC. Put that in your calculators, and here we go. Now let me go to one of my excellent students here. Ben, let me pick on Ben Seaman. Ben, unmute and say hi.
Good morning.
Hey, good morning. Ben, have you plugged in the numbers in this equation and gotten FAC for me yet?
For FAC, I got 806.2 pounds.
That's what I got. I got FAC is 806.2 pounds. And now see, we can get FAB. FAB, all you got to do is subtract the 806.2 from the 2000. Let me do that. And I'm getting FAB is 1,193.6 pounds. Okay, great. Now let's see what the answer book says. We're going to see how we did. This was problem 438. Go to the back there, look up 438. It was kind of tricky. Now, what the book says, need a little room here. They said FAC is 0.806 kip. But you know what? That's the same thing as what we got. We got 806.2 pounds. That's equal to 0.806 kips. We did good. And then the FAB, the book says, is 1.19 kips. The book says 1.19 kips. Now what we got is 1,193.6 pounds. But you know what? That's the same thing. We did great. And you guys have just seen a, what do they call that? A statically indeterminate problem. Well, there's one more topic today, but I don't want to erase that if you have any question. Any comments or questions? Well, okay then. There's one last topic today, and that's, I told you that deformation can be caused by stress. See, when you put that 2,000 pounds on there, it causes stresses in those wires. But deformation can also be caused by temperature. When you get things hot, they expand, wires expand. So let me show you that. I wish we had more time. We just don't have enough time together. Now this is called thermal stress. It's on page 155. And the topic is thermal stress. Actually, what they should have called this part of the chapter, they should have called it thermal deformation. And the equation for thermal deformation goes like this. You put a little T there to remind you that you're dealing with temperature. That's it. You might have seen this equation before in physics, perhaps. Now what they said isn't wrong. You're definitely going to pick up some stress when you make things hot. Now this alpha has got a name. It's called the thermal coefficient. No, it's called the linear coefficient of thermal expansion, or you could call it the thermal coefficient of expansion, but they have them in the back of the book. You go in the back of the book, and for A36 structural steel, it's 12 times 10 to the minus 6 per degree Celsius. But now in English, senor, it's alpha is 6.6 times 10 to the minus 6 degrees Fahrenheit. I'm just reading out of the back of the book. That's the thermal coefficient, or in their words, the linear coefficient of thermal expansion. I wish we had time to do a problem, but I'll just give you a suggestion of a problem. You know, when they lay the railroad, you make a little room here. I'm sure you're aware, and on bridges too, they leave a little space. They leave a little space between the rails. Each rail is laid down with a little bit of space, because see, when it gets hot, they expand, and there's deformation according to this equation. See that delta T is your temperature change, and L would be the length of your railroad. What's the word? Your rails, yeah. And then see, when they expand, then this gap closes. Whenever you hear a train go by, you hear this clickety-clack, clickety-clack, clickety-clack. You know what that is? That's the noise of the wheels going over those gaps in the rails. Now, if it gets really hot, on a really hot day, maybe up to 110 degrees, that can happen in Oklahoma. On a really hot, cloudless, sunny day with no wind, and the train goes by, you won't hear clickety-clack, clickety-clack, clickety-clack. Here's what you'll hear. Ready? That's it. There's no clickety-clack, because the rails, they've come together. There's no gap. Well, we're going to study that next, but it's sad, but our time together has come to an end. And unless you have a last comment, make it quick. I'm going to say goodbye.
Mr. Griffin,
Yes.
where did you find those values of alpha at the back of the book?
Oh, thanks for asking. Thanks for asking, Mohammed. In the very last page of your flap of your book, you will find those alphas.
Oh, I got it.
Yeah.
Thank you.
Yeah, you are so welcome. Well, guys, it's sad, but I'll see you on Tuesday at 9:30. Bye-bye, everyone.
Bye. Have a good one.
Bye. Have a
Bye.
good day.
You too.
Bye.
Bye-bye.